So everything from the beginning. Sorry. File, new model. Don't save anything. Okay. First thing, we're going to create a part. This is a 3D shell extrusions. We're going to create the pipe. That's the diameter is about 360. And so I'm going to create a circle from the center, and this is the. I'm going to put the radius. The radius is about, I don't know, let's say 160, comma 0. Done. And the length of the pipe, let's say 3D, is about 1000 millimeter. I like to use Newton and millimeter. Okay, so this is the pipe. Now I want to create some partitions in the pipe. Is it still recording?
Yeah, it's still recording.
Okay, so I'm going to create datum planes. You can create datum points, datum lines. You can create datum lines or points or planes. So I'm going to create datum planes from the principal planes that we have. So I'm going to the first one. I'm going to create an XY plane. And the XY plane, I'll give it an offset of 10 millimeter. And make sure that this is actually intersecting the pipe. Yes, indeed. So, done. And now I'm going to create a partition. Partition. Create face partition using datum plane. Select the datum plane. This is the datum plane. Create partition, and you can see now we have created the partition. Okay. Now I'm going to mesh it. I'm going to put here 10. Use S4R, mesh, and here it is. Well, let's make it 5. Might take forever to solve, so let's take it back to 10. Alright, so this is, now I would recommend doing it with 5. Okay? And then I need to create another part, which is the plate. Let's call it plate. It's a 3D planner. And let's say 600 by 600. So negative 300. Negative 300 to 300, comma 300. Done. Mesh it. Use the same mesh. And there it is. Material. And I am going to have one material, so elasticity. It's first 110. 1000 MPa, 0.3, and the plastic 300, 0, and you insert your stress strain curve, and let's say it's all linear, but in your case it's not going to be linear, and let's say up to 30% strain. So depending on the stress strain curve that you obtain. Now we're going to create sections. I have 3 sections. One for the plate, one for the pipe, and one for the used section of the pipe. So let's call this one plate. The thickness of the plate is going to be, let's say, 20 millimeter. Create another section, let's call it pipe. And the thickness of the pipe is about 6.9. Or you put the number that is correct for the pipe. Another section is pipe reduced. or reduced pipe. And let's put it 6.7. Okay. Now let's assign those sections. This will be the plate section. This will be the pipe section. And this part will be the pipe reduced section. Done. Okay, we created all our sections. Now we create the assembly. Bring part 1, bring part 2. Now, because of how I created those, I don't need to move them. No, I still need to move it. Yes, that's correct, because this is here. So I need to move this. You can, I know right away from this point to this point. And you have to click OK. So now the positions are fine. I need to create an interaction between both. Tie. Master surface is the plate. The brown or the purple, the brown or the purple, it's the purple side. And the sleeve is the surface as well. It's the pipe, but I want to be able to look at the pipe without the plate. So I'm going to go to View, Assembly Display Options, remove the plate, and now I'm going to select this and tie the rotational degrees of freedom for the shells if I want, and adjust the initial positions, just make sure that they are tied initially. Okay, and now bring the plate back in the view. Okay. Alright, so now we, in the steps, apply our boundary conditions. I have a symmetry boundary condition. This has a Z sim because it's a plane perpendicular to Z. And now this boundary condition will always be there. Now I'm going to create a new part, new step, loading or pressure loading. I always like to keep nonlinearity in the geometry on. Let's keep these as is and let's see what will happen. Now the pressure, 80% SMYS, P is equal to, well, the stress is equal to POD divided by 2T. This is 80% multiplied by the yield, which is 300. This is equal to the pressure multiplied by, okay, that's here. So P multiplied by OD divided by 2T is equal to 80% of the yield strength, which is 300. The pressure is equal to 2 multiplied by 6.9 millimeter divided by the outer diameter, which we said about 160, so 320 multiplied by 80 divided by 100 multiplied by 300. So pressure of 10.35 MPa. Alright, so pressure. I'm going to apply load, pressure on both this and this. No, this and this. Press shift to select both. Done. Brown or purple? It's purple. Applying the pressure on the purple surface. And the magnitude is 10.35 Newton per millimeter squared. Okay. Now let's make sure that this will run first. I'm going to fix one side here. I'm going to apply the boundary condition of displacement. I'm going to pick this side and fix y1, y2, and y3. And let's run it and see what will happen. Create a job, P1, continue, OK, submit. Input file processor completed successfully. There was no issue with the model. And now has completed successfully. Let's look at the results. Well, it's deformed. Let's look at the stresses, the von Mises stress. You can find the maximum von Mises stresses here, as expected around the weld. That's why this area we have to make sure that this doesn't fail. But the maximum von Mises stress is still very low. I'm going to look at view.
So here we don't have any stresses, right? This green part.
No, we'll see view options. We're viewport. Viewport annotation option. Font. Let's make it 14 for all these. So the green, yeah, we actually have less stresses in the green. That's correct. The maximum stress is about 260, around here.
Everywhere.
Yeah, everywhere. That's right. Okay, so this is what we expect. Now, then we want to apply the loading that we want, which is we're going to move that surface upwards, let's say. Alright, I'm going now to go to the model, create another step. I'm going to call it Tensile loading. Now this we want to do it in increments, 0.1 let's say. And the second boundary condition, I don't need it. I need another boundary condition. Okay, well actually...
Did you apply color part? Thickness increase?
No. But you could do it if you want. But I didn't do it.
Anyway, it didn't show any...
Well, let's see next. So let's just fix U1, U2 and move it in U3 a distance of let's say let's go 300 millimeters. Let's apply. So what's that remote strain? We have this, the distance is a meter. So this is 30% strain. Distance is a meter. We're applying 300 millimeter, so that's 30% strain.
Okay. So are you moving the plate?
I'm moving the edge of the plate.
In which way? In
the Z direction.
Tangent?
Yes.
Okay.
And fixing U1 and U2.
Okay. What about rotations?
I don't need, it's stable because looks stable because I fixed this in symmetry because this is symmetric.
Okay.
So the symmetry stabilizes the model. Now let's run it. Let's look at the results. Where are we now? Oh, so you see the plate is being moved.
Eccentric loading is on the
Yes. But now now that's the purpose of what you guys are doing is I don't want to be breaking the plate. I want to be breaking the pipe. So you have to design something by hand. And then based on the design, you do the analysis. Do you understand what I mean?
Design the plate?
Yes, by hand. By the design of the plate, just draw a plate, sit down with Greg, and see what are the options.
Okay.
How I can attach this plate. So for example, you might have a plate with a thick handle. I don't know how you're going to attach it. But design this plate, and based on that plate, based on that design of this plate, then you apply the load here. Okay? Let's say here I'm assuming that I'm applying the load on the surface. Okay? And wherever you apply the load, you make sure you fix U1 and U2 are equal to 0 and U3 is equal to displacement. But here, as you can see, I'm not applying the load. The plate is too thin. This is 20 millimeter and I'm applying the load too far. So I'm breaking the plate, not the pipe. And I want to break the pipe, not the plate. So you can see the maximum stresses is not on the pipe, it's on the plate. This is what we don't want. This is the purpose of the FEA. Maybe we should apply the load right here rather than here.
We can double the thickness of the plate, and then...
Yeah, but the problem with doubling the thickness of the plate is a lot of cost to get a 40 millimeter plate, and welding the pipe to a 40 millimeter plate is not good. And that's why you need to sit down, because you're just kind of heating only this part. The thicker it is, the bigger issues you have with welding. You don't have a uniform area. But the guys who are going to do the welding will make sure that welding is done properly. But we want to make sure that the plate is designed properly. Thickness should be small.
Okay. Thickness should be...
Maybe 20 millimeter. Or 30 millimeter.
It isn't... I mean, 20 is too thin.
But it's where I applied the load too.
Okay, too eccentric.
Yes. So you can see that this thing will fail right where we don't want it. We want this to fail. And I think this is done. Where are we? Oh no. Step 2, I could only apply 0.16 of the displacement. It's just taking, because now it's really deforming too much. Yeah, this is not what I want.
Oh, your applied displacement was
too much, yeah.
Okay, but it's not failing anyway.
Yeah, it's just failing here. So let's go back. Let's just scale it. And let's just see if we're going to use a plate that's really thick. So I'm going to go back to the sections, plate, make it 50, which is huge. I mean, this is a huge cost for no reason. So we've done the pressure loading. Here's the stresses after the pressure loading. And you can, not yet. It's going to take some time. I can look at the status file.
You can use that one.
Yeah, I know, but I would like to monitor it. It's the status file. Okay, so we had to start with 0.0625. Okay, now let's see what's
It's
happening.
calculating right now.
Yeah.
So slow.
What is slow?
Do we have too much too dense mesh, or last time it calculated so quickly?
No. It's just
What
at the
was it?
beginning. No, just at the beginning, it's not working. Now this is better. Just because the initial step is too high. The initial increment is too high. Now it's
No.
calculating.
Okay. Oh, okay. We want to see difference between pipe body and weld location, right?
Yes.
We don't see any.
Nothing yet. This setup might not let you do that. Maybe the only way is to apply the load eccentrically, but not so much eccentrically.
On one edge of the pipe,
Yes.
maybe? Pick one node, but how to do
Not
that?
one node, one area.
Partition again, how can we pick one area only?
Just do the partitions.
Many partitions on the plate, right?
Well, not many, just let's say partition. Or you can create a plate using solid elements and put everything that you're actually going to put on that plate. Whatever handle we're going to use. You have to talk to Greg to see how this attachment will work. Before you do this, you need to know how this will work.
But we don't draw the handle, right? We
You
just
can if you want. If you want to be detailed in yours, you can. But then it'll
Okay.
be solid elements.
solid
Like this plate would be a solid element, not shell.
together with handle.
Yes. But it's actually not bad here. Look. Because we used a very thick plate, it's not bad. It's going to...
Oh, it's failed here.
It hasn't failed yet because failure is at 500, so...
Look at the deformation.
It's actually failing in compression, not in the tension side. But if we put a crack, it's going to be fine.
Okay. We expect it to fail in tension sides.
Yeah.
So we should partition tension side and compression side differently.
Yeah. And you can...
Thinner,
in the future, we can do cracks. But for now, for the project, for the FEA project, and for the purpose of finding the force, we don't need a crack. Okay?
Okay. So we can do many detailed analysis of this.
Yes, but you don't... We need the analysis, enough details to answer our question.
Right now only how much force.
How much force and what plate connections do we need?
Thickness, plate thickness.
the whole setup of the experiment.
Yeah, eccentricity, thickness, and magnitude of force.
Yes, and how is the plate going to be connected to the machine? So this thing is failing in the compression side. I mean, it's not a compression side, but it's... This is very interesting. This is something that you guys should see. Why it's doing this here? When we're which side are we pulling? We're pulling on this side, and this is the area that's failing.
Yeah. Yeah, I mean, this is the compression side. It's failing first, and the compression.
But we're not doing compression. We're pulling upwards.
But this part is...
It's not under compression. Or maybe it is. I don't know.
I mean, it's rotating a little bit.
Let's look at the pipe before. Let's put the both deformations on top of each other.
It's almost buckling, right?
Ah, yes, it's almost buckling because this goes down.
How did you do that? You plotted both of them, okay?
Yeah. Allow multiple plots and put them on top of each other.
Mm-hmm.
Yes, true. There is compression. So you might wanna. This is compression because I used a very small area where I applied the load. If I use a bigger area to apply the displacement, it might not rotate that much. See that huge rotation? This huge rotation? Because I just picked a knife edge, basically. I picked the knife and pulled on the plate. But we need to understand how we can pull on that plate and let it rotate but not so much. So for example,
you can pull the entire
plate.
one half of the plate entirely.
Yeah.
Different ideas can be.
There are different ideas, but that's the purpose of your project. I'm not going to tell you what.
Yeah, we can document everything, for example.
So this case looks like that's not what we're looking for. Because we're basically I mean, it's not bad, but we're basically applying compression here. This is not. Actually, it's not. Maybe it's okay. Maybe it's okay. Let's look at the stresses. The problem is this compression has failed before the tension. So
it buckled.
It's because of the internal pressure, yeah. This is exciting. You shouldn't be sad. You should be happy. Look, this is very beautiful to work with.
Yeah, it's a lot of fun.
It's a lot of fun.
I could do that all the time, actually. I mean, you can create
whatever you want.
Thousands of pages work from that.
Exactly. You can do 6 masters.
Yes, 6, 7.
Yes.
Enough material for several people to graduate.
Exactly. You're going to be a very good professor at some point. All right. So
if he would let me, I would write 1,000 pages about that.
Yeah, but remember that at the end of the day, we want to do the experiments. After that, we can write however many things we want. All right. So that's good. Now, just notice that we couldn't finish. We could only apply 10% of the displacement because it buckled. It buckled and reached ultimate tensiles. We reached the maximum stresses here. Okay? And the internal pressure cannot push anymore. Every time it pushes, the thing wants to expand forever because it's yielded. Reaches its maximum. Okay? Alright, so you can stop now and I'll post it.